Professor Tarasankar DebRoy is a professor of material science and engineering, Penn State University. He has edited 5 books. His Google Scholar citations are 26,800 with an H index of 82. It is really a proud privilege for us to have Professor Tarasankar DebRoy as the plenary speaker. The floor is yours, sir.
Dr. Datta, thank you for such a generous introduction. What is smart metal printing and why we need smart metal printing? A piece of metal printing equipment can run up to $1 million and sometimes more. And process parameter window I will show you is rather large. So if you just wanted to do and see everything that you wanted to know, it's going to be a very long road. If you look at who are the big players in the world of 3D printing, you will not find too many startup companies doing metal printing because of the very large amount of capital equipment need, and also the consumables are not inexpensive. So the same old technique of developing technology is not going to work here. You need a new path. And that is what I mean by smart metal printing. And we need it because otherwise it is only going to be dominated by the large corporations, and smaller companies that generate employment and wealth are going to be not included in that technological boom. I want to keep the contents very simple. I want to talk a little bit about uniqueness, impact, and the problems faced by 3D metal printing right now, common defects, and also, most important, what mitigation techniques work that are dependent on emerging technological tools. Technological tools that make the world a little more flatter place, and I'm going to explain that later on. Especially, I'm going to show you how mechanistic modeling based on laws of physics can remedy common defects like lack of fusion, large residual stresses, distortion of parts, and sometimes in a new technology, we do not understand the mechanisms because they are still evolving. What do we do then? We use data and we use machine learning. What we have been doing at Penn State is that we have been augmenting, adding physics to machine learning. So it is not simply a question of data analysis, because the data analysis can be a long road as well. You need to collect the data, and the collection of that large volume of high quality data is not going to be inexpensive, certainly not in the domain of small companies. You need Rolls Royces and GEs for that. So what's the uniqueness? Think of the International Space Station. They needed a socket range, and NASA did not have any plans to a resupply mission. So what NASA did, instead of sending the physical part, they sent a computer program, an STL program, to print the part in 104 layers inside the space station. Something that was unheard of maybe 30 years ago. We could not have even imagined. So it has allowed us to think big and imagine better things. And this is just one example. On our part, we are trying to deposit compositionally gradient materials, and the purpose here is to make power generation more efficient and more reliable. Nuclear power plants were designed to have a life of about 40-45 years initially. High temperature creep remains a persistent problem. And if we can replace the dissimilar metal joints by a compositionally graded materials, we have shown that we can increase the creep life by hundreds of years. It's just unthinkable that we can do those things. And GE fuel nozzles are used now in their jet engines, and what used to take assembly of 20 different parts now can be made in one piece by additive manufacturing. They have opened up a completely new factory for doing just that, and it's making the jet engines more reliable. If you look at the distribution of revenues, they are coming from consumer products to automotive industries, to healthcare, to energy industries, to aerospace and marine. So where is the problem? Think how many alloys we use commercially. You will find there are more than 5,000 commercial alloys. And how many can we print? Just a handful. So what's going on? Where is the problem? Why can't we print thousands of alloys? Two issues. Failure to control structure and properties as we want it, and failure to control defects. That is what I want to focus on. But why on earth we cannot do that after hundreds of years of metallurgy and a very rich knowledge base of metallurgy? The knowledge base of metallurgy and welding, they are all incredible. But you see, look at the parameter space. Typical scanning speed can vary about 10,000 times. The power can vary 100 times. Cooling rate can vary million times. And metallic materials are notorious for being very sensitive to external impulses like cooling rate. So that's our problem. What's the consequence? A selected few are shown here. The most prominent problem is cracking, solidification cracking, if you will, but other forms of cracking, lack of fusion defects, residual stress, distortion, in extreme cases, delamination, as it is shown here, composition change, because alloying elements sometimes contain volatile components, and they selectively are vaporized so that the composition of the part can be different from the composition of the feedstock material, and surface roughness. So all of these problems can be solved using mechanistic modeling, where we know the mechanism, and where we do not, we have the other emerging tools. We have machine learning, but not the traditional machine learning, because the traditional machine learning has big problems too. I'm going to come to that. So what have we been doing for last many decades? We are developing relation between process, structure, property, and performance. That is what materials engineers do, right? So where is the problem? Why can't we use all the theory we teach our students to solve all these problems? Well, the problem is this conventional rich knowledge base still cannot give you a correlation between process variables and the product attributes. You need models for them. Okay? That's our fundamental problem. And emerging tools are mechanistic models where we know the mechanism and we can use laws of physics to quantitatively correlate process variables and the consequences of using a set of process variables in terms of product attributes and performance of the parts. Where we don't have the mechanistic understanding, we can fall back upon machine learning, that will give you quantitative correlation based on data. But as I explained to you, the data is not inexpensive. So we need new tricks here too. And that's what I'm going to focus on. I will give you 2 examples of mechanistic models to solve problems and 2 examples of machine learning. What we do in mechanistic modeling is shown here. We start with heat transfer because that dictates cooling rates and also the microstructures and properties and ultimately the performance of the parts. So what we do is we subdivide the domain into many cells, like in this case 250,000 cells. We solve for velocities, pressures, and enthalpy, 5 variables. We linearize them. At the end, we have little more than 1,000,000 algebraic equations. We do iterations to solve these problems. So 100 iterations any time step is about 1/8 of a billion equation. 1,000 time steps, we are solving 125 billion total equations. And today, even if you don't use quantum computers, if you use electronic versions of the computer, let's say a $600 laptop, it can solve 2 billion equations per minute. So in an hour, you can get a wealth of information that is solidly backed up by the theories of physics. You cannot go wrong. What's the output? What do we get from it? Almost everything you want to know and more. You can get geometry, temperature, velocity fields, cooling rates, temperature gradients, solidification growth rates, and a whole host of non-dimensional parameters that provide an insight that we cannot get by any other means. So there is no alternative if you want to know more of what's going on. Microstructural features, grain structures, topology, and all other things that you need to do other types of calculations like residual stress and distortion, thermomechanical modeling. So let's take lack of fusion defects. And we start with what we just calculated, temperature and velocity fields for making a part out of stainless steel 316 using thin layers of powder bed. 60 watt power, about 1000 millimeter per second, and we are making very thin layers, 0.03 millimeter. Sometimes we make these layers thinner than human hair, and we have parallel deposits that we call hatch spacing, 0.05 millimeter. If you take a cross section, they look like you have just cut a watermelon into half and sectioned it. So these watermelons can be put one after the other so that you can see how they are being deposited, and most important thing is that you see holes in them. These are lack of fusion defects. They have not had sufficient overlap between layers and between adjacent hatches. So that we need to modify, and we can do so for different process variables. We can reduce our speed, we can increase power, we can do few other tricks. They are also dependent on different materials. So we can actually have a pretty good handle on the effects of various parameters on reducing lack of fusion defects. This has been shown to be true for a whole host of commercial alloys. So this is one of the ways. Second thing is residual stress and distortion is a huge big issue. I showed you a picture of a part getting delaminated from the base plate. So what we are doing here is to make the process more accurate. Commercial codes like Abacus and ANSYS do not do accurate heat transfer and fluid flow calculation. They only do heat conduction equation. And heat conduction equation can be notoriously wrong because the primary mechanism of heat transfer within a fusion zone is convection. So if we ignore the primary mechanism of heat transfer, there are consequences. So what we do is we develop the heat and fluid flow model, we write a Python script, and then tell Abacus to take our more accurate temperature fields and then do the calculation. That way we can calculate correctly stainless steel for different types of process like gas metal arc additive manufacturing or directed energy deposition additive manufacturing or powder bed fusion. We can compare the consequences of using different machines, or we can look at different materials, like here we are looking at Inconel and here we are looking at Ti-6-4. So a lot of things that we could not think of doing have now become possible because of the emerging tools of the digital world. And where do you get hold of those tools? We did a review very recently, and this review you can get from our website, and there are lots of free programs for anyone that wants to learn. You don't need to write all your computer programs. They're all available, they are open source, they have worked out examples, and they all have applications in AM. One of the benefits that we can get in terms of residual stress and distortion of using those types of weaker routine, so we used what is called a random forest model to get the hierarchy of important variables. So here we are showing that the temperature difference between solidus and preheat. So preheat temperature has a great deal of influence over residual stress and distortion, more influence than other variables that are listed here. I'm going to explain to you what we mean by machine learning that is augmented with physics. So we are adding physics in order to reduce the volume of data, and that way we can prevent cracking using physics-informed machine learning. This paper is just published, so I'm going to explain to you what the problems are and how we are solving it. If you look at the important variables that control cracking, you will see a whole host of variables. And if you need to resolve these 12 variables experimentally, you will need 4096 data with a two-factor programming. But if you convert these to computed variables, then you will find all of these can be represented by only 4 variables. Your need for data will be much reduced. And not only that, you can actually do a regression and figure out which of these variables are more important and which of these variables are less important. So you know what exactly to compute. And you can validate it by developing a cracking susceptibility index for data that you can collect from the literature, and you can show that when the susceptibility values are greater than 0.5, your chance of getting a crack in your sample is much higher than otherwise. You can also develop maps. Here we are plotting scanning speed versus laser power, or preheat temperature versus laser power, and these are profiles of crack susceptibility index, so you can see whether you are in the safe region or you are vulnerable. You can also prevent balling defects that occur when you go too fast. And how do you do that? Again, follow the same principle, come up with a balling susceptibility index and validate that model so that you can figure out which variables are important and which variables are not so important. So what does it really mean? Based on scientific principles, use freely available computer programs to prevent all sorts of defects like balling and cracking for machine learning, residual stress and lack of fusion defects using mechanistic modeling. So what are the benefits of digital tools? You can improve quality without trial and error. There is no guesswork here. And engineers can choose process parameters without any empirical testing. You can do material selection, definitive material selection without any trial and error. So better product performance you can get. The meaning of what we do is that the expanded use of mechanistic modeling and machine learning will bring in a completely new path, a very different path than how welding and casting matured, without any empirical testing and with full backing of scientific principles. You will not need big test facility, you will not need special equipment, and you can dream for a better world. You are one of the largest technical universities in India. You can provide your students with ideas where the race, religion, ethnicity, nationality, job title, and affluence will not matter. So it will be a better and more inclusive world.
Thank you so much, sir. I request the participants to ask your queries to our professor.
Good morning, Professor. That's a nice presentation. This is Kumaran from Mechanical Department, SRM. Professor, the Sustainable Development Goals that's posted by UNESCO, did you relate this work also to such Sustainable Development Goals?
Not really. I recently authored a book with Sir Harry Badeshia, where we address the sustainability issues, but not here.
Thank you, Professor.
Yeah, good morning, sir. This is Ambihi.
Good morning.
It was a very nice presentation, and we were talking about the some index. With the index, we can correlate the cracks that is formed, no?
Absolutely right. Yes.
I think the previous slides.
Here is the index. This is the cracking susceptibility index.
Yes.
And this paper just arrived in Actamet, and I am told that the MRS bulletin, they are making a news item of our paper. I believe a commentary on our work will appear in MRS bulletin in the coming issue.
So how can we relate this index with the micro crack or cracks that is being developed?
The index is affected by solidification stress, the ratio of vulnerable to relaxation times, the temperature gradient to solidification growth rate or morphology factor, and cooling rate. So one has to do calculations of these four quantities in order to calculate a value of CSI. And once you have done that, you have a pretty good confidence of whether or not a sample is going to crack before you actually make a part. That's the beauty of it. You don't have to do it, spend your time, spend your money, and then find out it's cracking. You can do that before virtually.
Okay.
No empirical trial and error.
Okay. And it holds good for any type of material, no, sir?
It holds good for the database. In our case, aluminum database. Will it work for nickel-based superalloys? We are working on it. We have a paper coming in JMPT. It tells you on a mechanistic basis how to avoid cracking problem in nickel-based alloys. Solidification cracking particularly, not liquation cracking or other types of cracking.
Okay. Thank you, sir. Thank you for your nice presentation.
Most welcome. Thank you.
Any other questions from
Sir,
participants?
in case of additive manufacturing, are you using experimental data or simulated data for the machine learning?
We use everything we can get our hands on. We use experimental data collected by our collaborators. The reason we want simulation tools to be added to machine learning is because we don't want to use the regular machine learning that is so data intensive. And data is very expensive. It also introduces errors. Laws of physics do not lie. That's why we like mechanistic model when we can use mechanistic model. Unfortunately, we don't understand the complex mechanisms of metallic materials. As I said, they are notoriously sensitive to external impulses like thermal cycles, stresses, and other factors. So the simple answer to your question is we use both.